Hello and welcome to this presentation that describes the DMA transfer's hardware and software views. To start a DMA transfer, a request is required. This request can be caused by a hardware event, from a peripheral indicating that data are ready to be transferred, from a peripheral indicating that an update of its control registers is required, and from a peripheral indicating that a read of its status registers is required. A software request can also start a DMA transfer. This is typically caused by the CPU writing a control register of the DMA controller in order to transfer data from a memory-mapped address range to another memory-mapped address range. The DMA controller implements a programmable arbitration logic that enables the user to adjust channel bandwidth and latency requirements according to the following rules. The priority of the request is programmable from 0 to 3. Requests having the same priority are handled with a round-robin arbitration scheme. Time-sensitive requests should be assigned the priority 3, which is handled with a fixed higher priority scheme over the priorities 0 to 2. The residual bandwidth is shared by requests of priority 0 to 2 by implementing a weighted round-robin allocation for these non-time-sensitive channels. The different weights are monotonically resulting from the programmed channel priorities, the Q0 having the lowest weight. This slide and the 6 next ones will clarify the relationship between the software settings and the hardware transactions for the general-purpose DMA. The GPDMA supports a single transfer operation mode, the FIFO mode. A programmed transfer at the lowest level is a GPDMA burst. A GPDMA burst is a burst of data received from the source or a burst of data sent to the destination. Since the GPDMA has two AHB master ports, source and destination burst can be performed concurrently. The requested source burst transfer to the FIFO can be scheduled as early as possible over the allocated port, depending on when the FIFO is ready to get one new burst from the source. The requested destination burst transfer from the FIFO can be scheduled as early as possible over the allocated port, depending on when the FIFO is ready to push one new burst to the destination. Based on the channel priority, these ready FIFO-based source and destination transfers are internally arbitrated versus the other requested and active channels. This table lists the main characteristics of a GPDMA burst. A source and destination burst is programmed with burst length by the field SBL1, respectively DBL1, and with a data width defined by the field SDWlog2, respectively DDWlog2 and the GPDMA CXTR1 register. Programming SDWlog2 or DDWlog2 with binary value 11 leads to a user setting error. The addressing mode after each data, named beat, of a GPDMA burst is defined by SINC and DINC for source and destination respectively, either a fixed addressing or an incremented addressing with contiguous data. The start and next addresses of a GPDMA source or destination burst must be aligned with the respective data width. When the source or destination address increment mode is selected, the address is automatically updated at the end of a burst with the burst size in byte units, which is equal to the burst length plus 1 multiplied by the data width. When the burst length is 1, the burst can be also named as single. The programmed source and destination GPDMA burst is implemented with an AHB burst as is unless one of the following conditions is met. When half of the FIFO size of the channel is lower than the programmed source or destination burst size, the programmed source or destination GPDMA burst is implemented with a series of singles or bursts of a lower size, each transfer being of a size that is lower than or equal to half of the FIFO size. If the source block size is not a multiple of the source burst size but is multiple of the data width of the source burst, the GPDMA modifies and shortens bursts into single data transactions or bursts of lower length in order to transfer exactly the number of bytes equal to the source block size. If the source or destination burst transfer crosses the 1 kilobyte address boundary on an AHB transfer, the GPDMA modifies and shortens the programmed burst into singles or bursts of lower length to be compliant with the AHB protocol. If the source or destination burst length exceeds 16 on an AHB transfer, the GPDMA modifies and shortens the programmed burst into single data transactions or bursts of lower length to be compliant with the AHB protocol. In any case, the GPDMA keeps ensuring source and destination data and address integrity without any user constraint. The table lists the possible data handling from the source to the destination when the source data width is a byte. The source and destination data width of the programmed burst is byte, half word or word, as per the SDW log2 and DDW log2 fields. The user can configure the data handling between transferred data from the source and transfer to the destination. More specifically, programmed data handling is orderly performed with 1. Byte-based source reordering, 2. Data width conversion by packing, unpacking, padding or truncation if destination data width is different than the source data width depending on padding and alignment mode control field, and 3. Byte-based destination reordering. If destination data width is larger than source data width, the source data is either right-aligned and padded with zeros or sign extended up to the destination data width, or is FIFO queued and packed up to the destination data width. If destination data width is lower than source data width, the source data is either right-aligned and left truncated down to the destination data width, or is FIFO queued and unpacked and streamed down to the destination data width. If dbx equals 1, and if the destination data width is not a byte, the 2 bytes are exchanged within the aligned post-PAM half-words. For instance, the byte 7, byte 6 half-word becomes the byte 6, byte 7 half-word. If DAH equals 1, and if the destination data width is neither a byte or a half-word, the 2 aligned half-words are exchanged with the aligned post-PAM words. For instance, the byte 7, byte 6, byte 5, byte 4 word becomes the byte 6, byte 7, byte 4, byte 5 word. The table lists the possible data handling from the source to the destination when the source data width is a 16-bit half-word. The table lists the possible data handling from the source to the destination when the source data width is a 32-bit word. If SBX is equal to 1 and if source data width is a word, the 2 bytes of the unaligned half-word at the middle of each source data word are exchanged. For instance, bytes 7654 become bytes 7564. If destination data width is larger than source data width, the post-SBX source data is either right-aligned and padded with zeros, or sign extended up to the destination data width, or is FIFO queued and packed up to the destination data width. If destination data width is lower than source data width, the post-SBX data is either right-aligned and left truncated down to the destination data width, or is FIFO queued and unpacked and streamed down to the destination data width. This timing diagram highlights the relationship between the software configuration of a channel and the transactions that are generated on the AHB master port. An ongoing GPDMA transfer can be a data transfer, which includes source and destination burst transfers, or a link transfer for the internal update of the linked list register file from the next linked list item. 2 consecutive linked list items, or LLIs, are represented. First LLI number n, and then LLI number n+1. The data transfer is composed of a series of burst data reads, followed by burst data writes, because the GPDMA supports FIFOs. The GPDMA may modify and shorten bursts into singles or bursts of lower length, as explained in the previous slides. Each burst or single data transfer requires an arbitration cycle and a transfer over the AHB master port. The link transfer is composed of single data reads, each of them requiring an arbitration cycle and a transfer over the AHB master port. In addition to this presentation, you can refer to the other presentations on the GPDMA: DMA Overview, Autonomous DMA and Low Power Mode, DMA Linked List, DMA Circular Buffering and Double Buffering, DMA 2D Addressing, DMA Register File, DMA Error Reporting, and DMA Input-Output LLI Control.